Hello there, Mr. Sutton, bringing you the AB Calculus 6-4 classwork solutions on differential equation practice. For this problem, we're given some chemical reaction with a function that models the amount of substance present in grams at time t, and they're telling us when the reaction starts we have 10 grams present. Here's a differential equation that goes with this. For this part of the problem, they want us to find the line, or use the line tangent to our graph of f at time 0 to approximate the substance present at time 2. All right, so we're essentially looking for f of 2 when all is said and done. We're going to start by writing out a general tangent line approximation. So I'm going to write L of x equals, and for this function, since we're launching off at 0 here, I'm going to write f of 0 plus f prime of 0 times x minus 0. And now I'm going to fill in these different values to get my tangent line. So I can say then that f of 2, which I'm ultimately looking for, is approximately equal to the following. F of 0, they told us, was 10. F prime of 0, well, that's what I get when I plug in the point 0, 10 into my differential equation. Now, this equation only has a y value for us to plug things into. So we're really doing negative 0.02 times 10 squared. Well, 10 squared is 100. Times all this is going to give us negative 2. So we've got negative 0.02 times 10 squared, which I guess we'll evaluate in a sec. And then this is going to be 2 minus 0 inside there. So we have 10, and this is minus 2 times another 2, so minus 4 comes out to 6. And what units is that going to be? Well, since we're approximating the amount present, that's going to be grams. For this part of the problem, they want to know if, using this differential equation, the graph of f, the true graph of f, could resemble this graph down here. And then give a reason for your answer. So it's kind of hard to prove that the graph could resemble this. It's much easier to prove that it can't, and we definitely have a very good reason here. If you look at this differential equation, since y is being squared, that means that this stuff here is always going to come out negative no matter what, because you're always going to be doing a negative times a positive. So dy over dt then is going to be less than or equal to 0. I mean, I guess y could be 0, but it'll be less than or equal to 0 for all time values greater than 1. And honestly, all time values less than 1, but we don't really care about, before 0 for time. Looking at our graph here, is the derivative negative across this whole thing? Well, it's negative while we're decreasing, but then we start increasing. Since f, the true f, is never increasing, but this function here is, f cannot resemble this graph. For this part of the problem, they want us to actually find y equals f of t by solving this differential equation with the initial condition f of 0 equals 10. So we've got an output variable in our differential equation. That means we have to separate our variables before we begin. I'm going to start by dividing both sides by y squared to get it with the dy. So that's going to be, I'll call that y to the negative 2 times dy, or 1 over y squared, either way. And on the right side now, I'm going to multiply dt by both sides. So I'm going to multiply that by the negative 0.02 that's already over there. And I could have moved my negative 0.20, or 0.02 rather, over to the left side. But it's a lot easier to just leave it over there so I don't have to mess around with the y value. Because ultimately, I'm going to have to isolate y. So why put more stuff over there than I really want to? All right, time for some antiderivatives. On the left side, this bumps up to an exponent of negative 1. Dividing by that, we've got negative y to the negative 1. On the right side, this is a constant dt, so this is just going to be negative 0.02t, and then plus c. Next, we need to plug in the initial condition to find that c value. So I'm plugging in, let's see here, 10 for y, so this is negative 10 to the negative 1 on the left. On the right, I'm plugging in 0 for t. That zeroes out that negative there. So we just have c on the right side. And on the left side, we can call this negative 1/10 if we want. All right, time to plug c back in here. There's nothing to really resolve before I do that. I just have to plug it in. So there we go. All that stuff minus 1/10. And I still have to isolate y. I'm going to do this in 2 steps. First step, I'm going to multiply everything by negative 1. So that's positive 0.02t plus 1/10. And then I'm going to flip both sides of this equation to undo this negative 1 exponent. So I have y equals 1 over all of this stuff. Now you're technically done. You don't need to simplify this any further to get credit because you have isolated y. If you wanted to go a little bit further, this is really, let's see here, 2, or this is actually 1/50th if you have 0.02. This is 1/10. If we multiply everything by 50, numerator and denominator, we get 50 over, this would be t plus 5. So this is equivalent to this, believe it or not, but you could have left it unsimplified. For this part of the problem, they want us to determine whether the amount of the substance is changing at an increasing or decreasing rate and explain our reasoning. Well, here is the rate right here, dy over dt, with which our substance is changing. So we want to figure out if this itself is going up or down over time. So that means we need the derivative of our derivative, so our second derivative. Initially, if we take our second derivative, we get negative 0.04 y, and then a dy over dx, or dy over dt rather, after it. A lot of people are going to forget this, but you have to realize here, since the input variable is t, that's the only thing you don't have to do a d something over dt tail after. Since this is an output variable here, we have to differentiate implicitly and get a dy over dt. All right, well, this is almost enough to get what we need. I'm actually going to substitute this stuff back in for dy over dt, just to simplify this a little bit and put it solely in terms of y. So if I multiply this out, that's going to be, let's see here, we need 8 decimals, so 0.0008 times y cubed. And now I know that y is always positive for time greater than or equal to 0. I mean, you can't have a negative number of grams of something. So that means, therefore, that our second derivative is always positive for t greater than or equal to 0, which means that our substance is changing at an increasing rate since our second derivative is positive. On this problem, the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. So when it's first weighed, this bird weighs 20 grams, and we're calling b of t the weight of the bird at time t, days after it was first weighed. So we're given this differential equation, which basically tells us the rate at which the bird's weight is changing. But notice that the input here is the weight itself, the b value itself. So with that in mind, and given this y equals b of t is our initial condition to this differential equation, is the bird gaining weight faster when it weighs 40 grams or 70 grams? Well, the rate of change for its weight, again, is given by this differential equation, and these are b values they're giving us. These are both bird weights, so we just have to plug both of these in and see which one gives us a larger output. So we've got, I'm going to call this b prime of 40. That's going to be 1/5 of 100 minus 40. So 1/5 of 60 comes out to 12, and this is going to be in grams per day. So that's the rate at which the bird's weight is changing. And then we'll also do b prime of 70. That's 1/5 times 100 minus 70. So 1/5 of 30, which is 6 grams per day. So based off this, we can conclude the bird is gaining weight faster when it's the smaller weight of 40 grams. For this part of the problem, they want us to find the second derivative in terms of b, and then use that to explain why the graph of b cannot resemble this graph here. So let's start by getting that second derivative. To make my life a little bit easier, I'm going to go ahead and distribute this 1/5 now to my parentheses here. So that's 20 minus 1/5 b. And now taking the second derivative of this, 20 gets differentiated away. We just have negative 1/5 db over dt. I have to differentiate implicitly because this is an output variable, so I need that tail of that function right there. All right, so I haven't really done the problem yet. They said they wanted this in terms of b. I've got it in terms of db over dt. To go that one extra step, I need to replace db over dt with this expression up here, or this expression over here, either of those expressions. I'll just use this expression here because, I mean, they gave this to me, so I know this is correct for a fact. So we've got negative 1/5 times all that stuff up there. That's negative 1/25 times 100 minus b. And at this point, I could distribute, but I think it's actually easier to look at this if it's still factored out, because I notice that if b is anything less than 100, certainly anything between 20 and 100, then this parentheses comes out positive. Combined with the negative here, that's a negative overall result. So for anything between 20 and 100, certainly, our second derivative is negative. That means that the true graph of b should be concave down for this entire interval. But looking at this graph, we also have this concave up piece, which doesn't match what we see over here. So to summarize, b is going to be concave down the whole time, so it can't resemble the graph shown here, which has concave up parts. For this part, they want us to use separation of variables to find y equals b of t, given the initial condition b of 0 equals 20. So I look here and I see that I have an output variable in our differential equation. That means I need to use separation of variables to solve this. So I'll start by dividing both sides by 100 minus b. It's already factored for us. I'll just move this whole factor over to the left side. So I'm going to call that db over 100 minus b. On the right side, I'm going to multiply both sides by dt, so that'll be 1/5 dt. And now let me take the antiderivative of both sides. For the left side, I'm going to have an ln of absolute value of 100 minus b divided by this inner tail of -1, so that's actually negative ln absolute value of that. On the right side, this will just be 1/5 t plus c. Next, let me go ahead and plug in my initial condition. So for the b over here, I'm plugging in 20. Over here with this t value, that's going to be 0. And 0 times 1/5 is just 0, so we have c on the right side. On the left side, this is just negative ln of 80. All right, now it's time to plug c back in. But before I do that, let me take care of this absolute value. So in order to figure out whether I can just drop the absolute value or whether I have to negate the stuff inside, I take a look at my initial condition, and I see that I have an initial b value of 20. So that means that 100 minus 20, the stuff inside absolute value, is going to come out positive, which means I can just replace the absolute value with a normal parentheses and call it a day. So this will be negative ln of parentheses 100 minus b. And then on the right side, we still have 1/5 t, and now we have minus our c value of ln of 80. At this point, I need to isolate b. So my first step, I'm going to multiply everything by -1. So that's ln of 100 minus b equals negative 1/5 t and a positive ln of 80. And I'll just basically reverse the order they're being subtracted in to represent that. Next, to get rid of ln, I need to raise e to both sides. So I've got 100 minus b equals e to all this stuff. Now, e to the ln of 80, I can simplify that later on to be just 80 that I can bring out in front. I will still have e to the negative 1/5 t, though. So let me just go ahead and take care of that simplification now. So I have then 80 e to the negative 1/5 t. Next, let's subtract 100 from both sides. So this takes a lot of steps to isolate this. So there we go, 100 subtracted. And now finally, I multiply everything by -1 again to get b all by itself. So that's 100 minus 80 e to the negative 1/5 t. For this problem, I have this differential equation up here. And on this part, I'm just making a slope field for it using these 12 points they provided me. So let me start by making a table. I've got x values ranging from -1 to +1, and y values going from 0 to 3. So I'll make a table that has things lined up like that. And I'm going to go by columns here. So for my first column, this is where all the x values are -1. So -1 to the 4th, that's just going to be +1. So really, it's just going to be whatever the y value minus 2 ends up being. So we have a y value of 3 minus 2. That gives us 1. And 2 minus 2 is 0. 1 minus 2 is -1. And 0 minus 2 is -2. Next, I have an x value of 0. Well, that's going to zero out the whole thing. So all the way down, we've got zeros. And finally, we have an x value rather of 1. That's not going to change anything because whether you have positive or -1 being to the 4th power, it still comes out to just 1 out there. So I'm again going to have 1, 0, -1, and -2. All right, putting all that on my slope field now, I have a slope of 1 up here. Here I've got slope of 0. Down here, slope of -1, and -2 down here, a little bit steeper than -1. This whole middle column is just horizontal lines. And this last column here is going to be exactly the same as my first column, so we got 1, 0, -1, -2. On this next part, they're telling us that while the slope field in A is drawn at only 12 points, it's defined everywhere in the xy plane. They want to know all the points in the xy plane for which our slopes are negative. So we have to do a little bit of creative sign analysis with our differential equation here, thinking about what could make this thing negative or positive. Let's take it term by term, or factor by factor. So we've got x to the fourth here. Well, that's going to come out positive as long as x does not equal 0. So x to the fourth is greater than 0 for all x that are not 0. This next piece, y minus 2, that's going to be less than 0 if y is anything less than 2. So in terms of things that are going to make this negative, we can make this second thing negative by just making y less than 2. And we want this first thing to come out positive because we want a positive times a negative to give us a negative result. We can't make the first thing negative, so we're going to have to make the second thing negative and just keep the first thing positive. So we're going to get a negative overall result wherever x does not equal 0 and y is less than 2. So all points that meet this condition. On this problem, we want the particular solution y equals f of x for this differential equation, given an initial condition of 0, 0. Let's start by separating our variables. We see an output variable in the differential equation, so that means we have to separate. So I've got dy over y minus 2, and on the right side I've got x to the fourth times dx. Taking the antiderivative of each side, that's ln absolute value of y minus 2, equals, this will be 1/5 x to the fifth if we bump that exponent up and divide. And don't forget the plus c. Next, let's plug in our initial condition. So I have ln of absolute value of 0 minus 2 equals 1/5 0 to the fifth plus c. Well, on the right side, this just zeroes out, leaving us with c. On the left side, we have, well, let's see, this is ln of absolute value of -2, so that's actually ln of positive 2. Now to plug positive 2, or positive ln of 2 back in for the c value. Before we do that, though, we need to resolve this absolute value here. So to do that, looking at my initial condition, I see my initial y value is 0, which means that the stuff inside my absolute value, the y minus 2 here, is going to come out negative. That means that I have to negate everything inside here. So negative y plus 2, or 2 minus y, either of those, if I want to keep this ln doing what it's supposed to do and not end up with negative values inside the ln function. We still have the 1/5 x to the fifth on the right side, and to that we're now adding our c value that we just found of ln of 2. Just a couple more steps. We still need to isolate y, so I'll start by raising e to both sides to get rid of this ln. So that's 2 minus y equals e to all the stuff over here. And this next step is kind of optional, but I don't know, I kind of feel fancy when I do it. So we can split this up into e to this first term times e to the ln of 2. And e to the ln of 2 is really just 2. So we really just have 2e to the 1/5 x to the fifth. Again, totally optional, but makes it look nicer. And then we can subtract 2 from both sides. Finally, we're going to get y by itself by dividing by a negative. So I'm just going to write this as 2 minus 2e to the 1/5 x to the fifth. Or negative that plus 2, either way. And then we're done. For this problem, we have this differential equation, and on this part we're just trying to get the slope field for these 12 points. So let's start by making a table. I've got x values from -1 to 2, and y values from 0 to positive 2. So here's my table with all those values in it. For my first column, this is where x is -1. So -1 is just positive 1. So really it's just up to the y value to figure out what my values are here for the slope. So I've got the y value 2 squared over 2. That's going to be 2. And then we've got 1 squared over 2 is 1/2. 0 squared over 2 is just 0. Next column, all the x values are 0. That's going to zero out this whole differential equation. So that's just 0 all the way down. Next column, the only difference between that and this first column is that now multiplying by -1 instead of positive 1, because the negative isn't happening anymore. So now I've got -2, -1/2, and still 0. And then finally here, Well, that's just going to be this last column multiplied by 2, because now I'm multiplying by negative 2 here instead of negative 1. So this is going to be negative 4, negative 1, and 0. Graphing all those out, I've got up here a tangent line of 2, so that's going to be like so. And then we've got 1/2, a little less steep. 0 is a horizontal line. This column here is going to be all horizontal tangent lines because they're all slopes of 0. For this next one, I've got negative 2, negative 1/2, and 0. And finally here I've got negative 4 is going to be even steeper, and then negative 1 less steep, and then 0. For this part, they want us to write an equation of the line tangent to the graph of f at x equals negative 1. So there's two ways to do this. One is to say like L of x equals, f of a plus f prime of a times x minus a. You could also just use point slope formula, but you're going to have to find the slope either way. So to find my slope, I'm going to plug the point negative 1 comma 2 into my differential equation. That's going to be negative 1 times 2 squared over 2. And we actually calculated this when we were doing our slope field in part A. So this is going to be positive 4 over 2, which is 2. Plugging this into point slope now, I can say y minus 2, the y value, equals my slope of 2 times x plus 1, or x minus negative 1. For this part, they want us to figure out the actual solution, the particular solution for y equals f of x, given this initial condition of f of negative 1 equals 2. Looking at my differential equation, I see I have a y in the differential equation, an output variable, so I need to use separation of variables here. I'll start by dividing both sides by y squared. That's y to the negative 2 times dy equals, and now I'm multiplying dx to the other side. So I'll call this negative 1/2 x dx. And now it's time for some antiderivatives. On the left side, this bumps up to a negative 1 exponent. Dividing by that, I've got negative y to the negative 1. On the right side, this bumps up to a 2 for the exponent. Dividing by that, I've got negative 1 over 4 x squared plus c. Now it's time to plug in that initial condition. So on the left side, I'm plugging in 2 for y, so this is negative 2 to the negative 1. On the right side, I'm plugging in negative 1 for x, so negative 1/4 times negative 1 quantity squared plus c. And on the left side, this is really negative 1/2, which it'll be convenient to think of as negative 2/4. Over here, I've just got negative 1/4. Adding that to the left side, I have negative 1/4 overall for my c value. And now I'll just plug that back into the general solution up here. I'm almost there, but I still need to isolate y. So I'll start by multiplying both sides by a negative, and actually, while I'm at it, after I multiply by that negative, I'm going to move these two into one big fraction. So this is going to be x squared plus 1 over 4. And the reason I'm bothering to do that is my next step is going to be to flip both sides of the equation to get rid of this negative 1 exponent. So essentially raising both sides to the negative 1. So that gives us y equals 4 over x squared plus 1.